90% of engineering involving sounding, which is moving, so dynamics of a bridge, for instance, is studied with the mechanism and bridge. Okay? So, of course, we have a limit. We are studying linearized relations. So when you have no linear oscillations, then you need not approximated form for conjugation. Okay? So I repeat what we did, because you must understand it correctly. We have chosen a motion which is rest. So we have a equilibrium configuration, and we have assumed that the system we are studying obeys the principle of the destruction. So the ordinary differential equation, which is verified by every motion, the system of differential equations, because there are many of them. How many? Exactly the number of equations which we need. So as many as degrees of freedom. Okay? So every motion must verify this set of differential equations. Okay? If Q naught is an equilibrium configuration, then, so if Qt equal Q0 is a solution of Lagrange equation, then dl over dqi calculated in Q0 has to be equal to 0. So, in order to characterize the equilibrium configurations of your system, you need to study this equation. This equation is nonlinear in general. However, it is an equation whose unknown is a configuration. So the unknown is a set of n Lagrange parameters. So it is a relatively simple problem, because the unknown is not a function. Here, the unknown is a function of time. Here, the unknown is a set of n Lagrange parameters. Okay? Now, I try to draw a picture, but of course, it's just suggesting something. If Q0 is a solution of this problem, we call it a stable equilibrium configuration if, when you choose a Q bar and a Q dot bar, an initial configuration Q bar and an initial velocity, Lagrange velocity Q dot bar, which are both small, so Q bar and so Q0 minus Q bar and Q dot are small. If this condition is verified, then for every t, Qt minus Q0 remains small, and Q dot bar remains small. Of course, this is not a mathematical definition. We could, and maybe we will, if I come towards it, maybe we can decide if we will be there to go into more details in this layout of definition. The idea is the following. If I am here, this is the equilibrium configuration. If I place my system close to this equilibrium configuration, and if the initial velocity is small enough, then the motion will remain here. Without going out a given ball, and it will have a small velocity. Okay? This is a stable equilibrium configuration. If you want to ask yourself why this was defined, think about the pendulum. Think about Galileo pendulum. If you have the weight with an inextensible part suspended at a pivot which allows rotation, if you move this a little bit, and if you give to it a small velocity, then it will remain always there, in the neighborhood of this equilibrium configuration. If instead you place the pendulum in this other, which is still an equilibrium configuration, a very small perturbation of the system starting from the equilibrium condition will induce a motion which goes very far with very high velocities, very far from your equilibrium configuration. So, why we are interested? Why we were interested in this? We're interested in this because if we know that Q0 is a stable equilibrium configuration, then we can write the motion using this formula. Where epsilon is suitably small. And in all calculations we will perform, we can decide to neglect every square of epsilon, cube of epsilon, every power higher than 1. So what we can do is that linearize can linearize every equation, stopping every Taylor expansion at the first order. Okay? So what we did now, I will not repeat another time the calculations. What we have done, for instance, we have written dl over dqi, which is a function of q and q dot in general. We have written as a zero order term, so let us call it f0 plus epsilon f1. Okay? And we painfully calculated this. So, this f0 and f1. Okay? As we know that q0 verifies this condition, f0 is 0. Okay? So, at the end of the story, this equation, Lagrange equation, can be written in this way. A term L0 plus epsilon L1 plus epsilon square L2 plus equals 0. Okay, so please revisit the calculations we have already. I have already shown you with this using this slightly different one. So we take this, we assume the expansion we have at the top, and we expand this equation. L0 equal to 0 reduces to this equation. So it is verified for equilibrium configuration. However, to be sure that this term is negligible here, is really equal to 0, is small compared with the other one, you must know that for every subsequent time instant t, the representation for qt I put before is found. So you must know that you remain always in the neighborhood of q0 for every subsequent instant. Otherwise, some of these terms could become important. Okay? Okay, this is a very mathematically speaking, this is a very subject, and you need, for understanding all technical details, you need much more mathematics, which is reasonable for somebody of your age. Okay? What is important is that you know that this assumption is not always valid, and you must be careful. You need to know a priori that your motion is limited in the neighborhood of your equilibrium configuration. And this is what characterizes stable equilibrium configuration. Then what we did, we wrote this L1, which has to be equal to 0. And what we wrote? We wrote the matrix of mass M Q double dot equal minus an Hessian matrix Q, okay, plus eventually a gyroscopic or dissipative matrix G Q. This is what we have done yesterday. So, actually, in our calculation, if you remember, we are epsilon times this. writing this term in the expansion. As you can neglect all higher order terms, this you can factorize this example and your equation reduces. This is the equation of the motions in the neighborhood of Q0. So this is what is called the equation of small motions. Okay? So this is the resume of what we have said yesterday. Not complete yet. But we have already introduced the concept of eigenvector, eigenvalue. Okay, and we already discovered that n is symmetric, definite positive, and h is symmetric, definite positive. Now, let us forget for a while G. So we start studying n q double dot equal minus h q. Okay. Of course, m is, we said, symmetric, definite positive, because it is related to the kinetic energy of our system. Okay, it is worth to say this as well. So we repeat what we said. Every Lagrangian is admissible for a least action principle. However, this system of equations could not be the system of equations for which we have the existence and uniqueness theorem proven by Cauchy and Usa. If you remember, you need that dl over dq dot I dq dot h, this matrix must have an inverse always in order to transform this equation into a system of equations for which the existence and uniqueness theorem by Cauchy holds. Okay, this observation is due to Legendre. Okay, so not every Lagrangian is good, or at least not every Lagrangian is good enough that we can apply to Lagrange equation the existence and uniqueness theorem which we have. If this symmetric matrix has an inverse, then the evolution equation is well posed, which means that you can forecast fusion using this equation. If you give me initial data, so initial position and initial velocity, and if this matrix has an inverse, then you know that there is a unique evolution, and you also have a unique algorithm for calculating this evolution. This is the reason for which French mathematical physicists were so excited when Lagrange wrote these equations. This is what is called mechanical determinism. This is the basis of illuministic vision of the world. Give me initial data, I will tell you what will happen in in every future instant. So I can forecast everything. As I told you already one time, if you also accept the atomistic vision of the universe, so if you accept that the universe is made by atoms and will be large, but could be finite. For knowing what happens to the universe, you need to know what is happening to every atom. So you write a suitable large number of equations, and you can forecast what will happen to the universe in every instant, if you know the initial data. Laplace, Lagrange, Legendre were reasoning in this way. By the way, this is not new, because Archimedes spent a lot of time and wrote a book for calculating the number of grains of sand which you can pour in a sphere whose center is the sun and whose radius is the distance between the sun and the most distant planet in the solar system. Why he was interested in getting this number? He wanted an order of magnitude of this height. He wanted to understand how many degrees of freedom can have a universe. Okay, I will tell you later the story how we discovered this ancient book. Okay. Okay. So, if you have a well-behaved Lagrangian, this system of equations is suitable for forecasting every future event. Okay? However, Hamilton conjectured that for mechanical systems you have a kinetic energy, which is a quadratic form in terms of Lagrangian form, and you have a potential energy, which depends only on the configuration. Okay? So, a mechanical system, this is the conjecture of Hamilton, is described by this Lagrangian. This is an hypothesis. Okay? If you accept this hypothesis, M can be called, is related to the masses, so the coefficients of quadratic form of T, and H is the Hessian matrix of Newton. We did this calculation. Okay? So, in the particular case of a mechanical system, you have that the small motion in the neighborhood of an equilibrium condition is given by these Now, we stop for a moment the epistemological considerations. So we stop talking about philosophy of science, and now we discuss how to solve this system of equations. Okay? exists. So we can write Q double dot equal n minus 1 H Q. And this proves that our system is a system of ordinary differential equations in the normal form. You have higher order derivatives equal something depending on lower order derivative. This is, remember, we said that a system of ordinary differential equations has this structure, where f is Lipschitz continuity. Okay? And we have learned how to reduce to the first order a system of higher order. Okay? So, of course, y belongs to R and K. Okay? So, this is a well-behaving system of equations. And if you give Q T0 equals Q0 and Q dot T0 equals Q dot 0, so if you give initial data, then you know Q of T at every subsequent instant. Now, the problem is, how do we get this solution? Of course, one can use the Cauchy-Busta method, and that's it. The beautiful feature, property of this linear system of equations is that you can reduce the problem of finding the solution of this system to a problem in linear algebra. So, a problem which is computable, algorithmic, and it is the easiest kind of algorithmic solution which is available. Okay? So, which is the simplest matrix you can imagine? The matrix of our dreams is diagonal. Let us think. If you have Q double dot equal lambda Q, and lambda is a matrix lambda 1, lambda 2, lambda n, 0, 0, 0, 0 everywhere. So if you have a diagonal matrix, the diagonal matrix is the matrix of our dreams. Why? Because this set of equations, I hope that you agree with me, this equation will be written in this way. Q double dot 1 equals lambda 1 Q 1. Q double dot 2 equals lambda 2 Q 2. Q n double dot equals lambda n Q n. You agree with this? If, for a reason, this matrix is diagonal, then this apparently complex system of equations becomes this very simple system of equations. Maybe it is worth, you must learn how to use indices, matrices, systems of equations. It is not trivial. So I will use pure notation. By the way, I don't know if it was the first one in the world, but the first book written in Italian where you find these reasonings has been written by you. With this heavy notation. So what means this? Let us write Q double dot equal BQ. Where B is a matrix. Okay? This means Q double dot 1, Q double dot 2, Q double dot n equal B11, B12, B1n, B21, B22, B2n, Bn1, Bn2, Bn, and here you have Q1, Q2, Qn. Okay? This is this equation written in components. So this is exactly the same, but I'm lazy or I'm clever with truth. And I don't like to write this enormous formula, and I invented a quick way for writing it without, this is important, without losing any information. This is what is important. Clever notation means exactly the same in a more effective way. Okay? Now, if I write the equation, I write Q double dot 1 equal this times this. So what I get? I get Q double dot 1 equal B11 Q1 plus B12 Q2 plus B1 and Qn. Q double dot 2 equal B21 Q1 plus B22 Q2 plus B2n Qn. And at the end, I get Q double dot n equal Bn1 Q1 plus Bn and Q. So what you have? That the second derivative with respect to time of every Q depends on the value of all components of the vector. So Q double dot I depends on the value of Q1, the value of Q2, the value of Q4. So this is what is called a coupled system of ordinary differential equations. In the situation of our dreams, the system becomes uncoupled. Because if you have a diagonal matrix, all coupling terms are 0, and you get Q double dot 1 equal lambda Q1, Q double dot 2 equal lambda 2 Q2, Q double dot n equal lambda n Q. Wonderful. Okay? And this wonderful means that what you have studied in the class of physics, the equation of the harmonic motion, is more general than what could be imagined. Okay? Now, the problem is, can I reduce this system of equations to this system of equations, or if you like, to this system of equations? There is a beautiful theory nowadays not used for engineers, which tells you that given a matrix with a suitable transformation, you can always diagonalize it. Now I will try to explain you what this means exactly. Okay? So at the end of the story, we will prove that this system of equations, so this complex system of equations, indeed can be reduced to this system of equations. So actually, this is the system of equations more general for small motions. This is wonderful. Okay? So let us see. I have a reasoning which is very simple. If you have a diagonal matrix, which are the eigenvectors and which are the eigenvalues? It's trivial. You have lambda 1, lambda 2, lambda n, 0, 0. And you want to get that this matrix applied to a vector is lambda times the same vector. So if I have 1, 0, 0, you do the calculation, and what you get? Lambda 1, 0, 0. Which is lambda 1 times this. So if you want to diagonalize a matrix, you must find its eigenvectors and its eigenvalues. Okay? Last time I have already shown you that I can give you a solution of this equation if I know an eigenvector of B and its eigenvalue. Now we are doing a more general reasoning. How many eigenvectors you need for diagonalizing a matrix? You need exactly n. Remark, it could be that lambda 1 is equal to lambda 2. The eigenvalues may be equal, or equal, some of them equal among themselves. But you need as many eigenvectors as number of eigenvectors which you need. Otherwise, you cannot memorize the matrix. Okay? So my suggestion is, we gave you already some book where you can find everything presented with eigenvector and eigenvalues. I am giving you a way for interpreting this mathematical theory in the context of small motion we are considering now. Okay? So what we do? The following trick. We imagine a new system of coordinates, which we call normal coordinates. We call it psi. So psi is equal to psi 1, psi n. Okay? And we assume that Q is given by a matrix P times psi. So we do what is called a change of coordinates. So instead of using as a system of coordinates Lagrange coordinate psi Q, we use as a system of coordinates the coordinates psi. Okay? And we assume that this change of coordinates is given by a linear transformation, which we have called P. Okay? This is a generalization of something which you have already known. If I have this basis, or if I have these other bases, and I have a vector, I can represent this vector in the basis E1, E2, or I can represent the vector in the basis E1 prime, E2 prime. And when I change the coordinates from one reference to the other reference, I have such a linear transformation. What I'm trying to do is to find a clever system psi. A more efficient system of coordinates psi. Okay? Good. Then, of course, psi is equal to P minus 1 Q. We are assuming that P has an inverse matrix. Okay? So there is a one-to-one map function between psi and Q. Now, I use this formula if I have Q of T, this is equal to P psi of T. Consider this. P is independent of time. Okay? So psi of T is varying with time, Q is varying with time, but the transformation matrix is independent of time, which is very useful for what we are doing. Then Q dot is equal to P psi dot. Okay? And therefore Q double dot of T is equal to P psi double dot of T. Okay? We are very close to a very important result. Why? The equation we want to solve is this one. So I have Q double dot equal minus M minus 1H Q. I replace P sine double dot. This is equal to minus M minus 1H P sine. Okay? Then I discover that I can multiply everything times P minus 1. So at the end of the story, I have sine double dot equal P minus 1 minus M minus 1H P sine. This is simple linear algebra. This is the system of equations which we had before, transformed in the new coordinate system. Now, what we will gain in this? This new matrix can be chosen to be diagonal. This is what we get. You know why? There is a beautiful thing which tells you, give me a matrix B, which is the product of the inverse of a symmetric definite positive matrix times a definite positive symmetric. There exists a P such that this new matrix is diagonal. Not only. This theorem tells you how to calculate lambda and how to calculate P. And these calculations can be performed using trivial linear algebra operations. I tell you the final result, and your work is to go in your book of linear algebra, or in the book which we gave you, or in both, and to check the technical details, which are now very easy. P is a matrix built with the eigenvectors of the matrix B, or M minus 1H. So P has as columns the eigenvectors of your initial matrix M minus 1H. So again, if I want a matrix n times n, which is invertible, how many eigenvectors I need? Exactly n. And they must be independent. So I need a new basis of my space of coordinates, and in the new space I need to find, in the new basis, each element of the basis is an eigenvector. So I need a basis of eigenvectors. Okay? Do you know which is the role of eigenvectors? They give you the lambdas in the diagonal of diagonalized matrices, as we suspected when we did the calculations before, because lambda 1 is the eigenvalue of 1, 0, 0, and so on. So, in order to diagonalize a matrix B, I need to find a basis of eigenvectors and the corresponding eigenvalues. Okay? How do I calculate eigenvectors and eigenvalues? Through shape-ability theorem. B u equal lambda u, where u is different from 0. So I have B u minus lambda identity u equal 0. This is trivial, right? Identity applied to u is u. Then I can factorize on the right. So what I get? B minus lambda identity u equal 0. Okay? Here, the useless theorem of Cauchy-Capetti comes and gives you an interesting result. I have an homogeneous linear system. This is the matrix of coefficients. This is the unknown vector. This matrix times u equals 0. U is non-zero. So it's not vanishing, because we need to build P. If you have a column of P made of 0 vectors, you will never be able to find the inverse. Okay? So the rank of B minus lambda identity cannot be n. Because if it were n, then only the trivial solution were possible. The only solution of an homogeneous system with a matrix of rank n is the vanishing solution, the trivial solution. So, try to revise these results in detail, because otherwise you will never be able to study the oscillations of a bridge. I will tell you how this is related to the oscillation of a bridge. This animal implies the determinant of B minus lambda identity equals 0. So I repeat, in order to find an eigenvector associated to a given eigenvalue, this is the equality which I must take. This equality implies this and that. Applying the Shea-Capelli theorem, the Shea-Capelli theorem tells me that the solution is unique if the rank is maximum. Okay? If the rank of the matrix of coefficients is maximum. Okay? The unique solution for a homogeneous system can be only the trivial solution. Everything is simple. I want a solution U which is different from zero. So this determinant must be zero, because this is the only way which is possible, logically possible, to have the rank of this matrix smaller than A. Okay? Okay. Now, before stopping this mathematical discussion, we must discover the following. This equation is a polynomial equation of order n for lambda. This polynomial has been studied by Gauss when studying the motion of planets. And for this reason, it is very often called circular equation. Circular equation, essentially, in Latin is related to circular, right? This equation was used for calculating the circular disturbances on the motion of planets related to the gravitational interaction with the other planets. If somebody tells you that studying the motion of the planets is useless for engineers, in practice, are you building solar systems? You are not. So somebody very clever who decided, and indeed this happened, that you don't need to study the motion of planets, even the simplest one. You know, for 150 years, everybody became an engineer after having studied, among many other things, the motion of one planet in the solar system. You need 4 hours of calculations. You learn a lot of things. One morning, a clever engineer decided this is useless for engineers. Imagine that we can go forward and we can decide that this is useless except for experts in celestial mechanics. So we don't teach it anymore. Now what happens? That an engineer one morning built Tacoma Bridge. And it was very clever. So clever that a small wind started imposing wider and wider oscillations to this bridge until the bridge collapsed. Do you know which is the equation of motion of this bridge? This. These are the equations. Do you know how you must design the bridge? Choosing lambda very far from the lambda relative to the wind. So ask to these deep and clever intellectuals who decided that the motion of planets is useless, how we could imagine all this theory without the knowledge given to us by celestial mechanics. You can never tell what you will need. You need a general intuition. One could say an engineer is not does not. An engineer is not required to write an elegant text in any language. So why teaching him conjugations? You teach him 300 words and you have a complete engineering. Culture is a whole. I quarreled with an American mathematician whose name is better not to tell you why I'm really recording manager. He claimed that he didn't know who Napoleon was and he was proud of it. Because being a mathematician, he doesn't need this knowledge. I am worried about this, and this, in my opinion, is very dangerous. Terribly dangerous. This equation, the secular equation, is an equation which you can use to find lambdas. So you write B11 minus lambda, B12, B1n, B21, B22 minus lambda, B2n, Bn minus lambda. Okay? I hope that you heard about Laplace rule for calculating a determinant. Okay? Laplace needed it for studying the motion of planets. Okay? Today, for instance, the first problem, you calculate this times the complementary minor. So times this determinant. Okay? Then this with the sign minus times the complementary determinant. At the end you get this times the complementary. How many lambdas you have to multiply one to the other? If you take this, you have one lambda here. Then you have this, and this complementary determinant. So you have n times lambda. And then you have many coefficients for lambda to the minus 1, many coefficients to the lambda minus 2, and n minus 2, and so on. So actually, this determinant is a polynomial in terms of lambda. The higher order is minus 1 to the n lambda to the n, plus coefficients equals 0. want to study the set of eigenvalues of a given matrix, you need to be able to solve a polynomial equation of degree n. And you must know that you can have at most n solutions. And you have to find an algorithm for finding this solution. Okay? This is what comes of this image. When you draw for him a structure, look how powerful this software. It takes finite elements. It reduces the problem to a finite dimensional system. It writes this equation. It finds eigenvalues of this matrix. Then when you have found one eigenvalue, this one, this matrix is known. So you solve this equation and you find the corresponding eigenvectors. The plot which Ivan has shown you is the shape of motion relative to a given eigenvector. I will show you the correct formula. Okay? So, I've given to you some details. I have left to you some other details which you have got to read by yourself. Okay? Why? Because I want to conclude the story. I have spoken about a common bridge. I must tell you exactly where is the problem. So, imagine you have found P. Okay? The equations are sine double dot I equal lambda I sine I, not sum over repeated indices. This notation is failing in this context. Okay? So this means sine 1 double dot equal lambda 1 sine 1 and so on. Okay? The solution of this system of equations, you know, it is a linear combination of cosine and sine, where this frequency is related to the square root of lambda. You know this idea. So should I tell you, do the calculation? If you consider cosine, you do the first derivative, you get sine, you do another derivative, you get cosine. You must be careful with signs. So the second derivative is equal to the function. The same is for sine and cosine. The sign of this animal is given. This is definitely positive. This is definitely positive. You have a minus, so all these are minus with positive lambda. Okay? So the solution of sine are periodic solutions with given frequencies, one for every lambda. So you know the natural frequencies of your system. It is vibrating with this n frequency. As the system is linear, the generic motion of your system is given by Q of t is equal to P of psi of t. Okay? So what do we do? Psi 1 of t, the eigenvector u1, plus psi 2 of t, the eigenvector u2, plus psi n of t, the eigenvector u2. Okay, so you have that this system is oscillating with the frequency 1 and the mode u1, with the frequency 2 and the mode u2, the frequency n and the mode un. Okay? If you have an external force which is applied to your system, you have to add in the Lagrangian one term. You do all calculations you have done, and at the end of the story, you will get Fi of t. In every equation of motion, this will be the Lagrangian component of externally applied motion with respect to the Lagrangian coordinate psi. Do you know what happens if Fi of t has exactly the same frequency, the same natural frequency of this harmonic oscillator? Yeah, what is called resonance. The solution is not sine cosine, but it is t times sine cosine. So its amplitude goes to infinity. So it is not valid anymore the assumption of small oscillation. So all these collapses, all the theory is not applicable. And you get a strong indication. You may have one of these normal Lagrange parameter which tends to infinity. So the value of Q of t minus Q0 can go to infinity. So you can go very far from the equilibrium configuration you have seen. Remember, this can be true even if the absolute value of Fi is very small. So you can have a very small external load. However, it lasts long enough to transmit to your iPhone enough energy to get very large oscillation. You know this. You experience this. When you are children, I don't know how to say English. Altalena come si dice?
Pendulum.
You know, these, you have two ropes as seen. You sit on it and somebody is pulling you. How is pulling you? With a given frequency, which is device. And the amplitude of oscillation can be large enough, and actually at a given moment to stop, because it could become very dangerous. Okay? So, with the linear analysis which we have started, you can detect the kind of external loads which are dangerous. Okay, so the final, what we learned by this story, what this story is teaching us. The designer of Tacoma Bridge was a practical engineer. Okay? Something like 100 years before he was born, mathematicians had already studied resonance. Not only, some engineers had already exploited resonance. Do you know what a radio is? A radio is a device in which you change the internal frequency of resonance of the antenna for receiving a very small signal which is amplified and you hear the voice. So, Hertz, Marconi, the inventors of radio, had already exploited resonance. However, you know, this American engineer, whose name I couldn't find, and this clear, he's not very happy. So he has hidden his name. Okay. This engineer was a practical man. Okay. He built a very rigid, strong structure, and he knew that the wind there was not very strong. It was not a tornado. It was a breeze. Okay. So he said, how can the breeze destroy my beautiful bridge? If the breeze had the habit of arriving with a given frequency, and if you were so stupid not to study resonance, and your system, your bridge, had exactly the natural frequency of your breeze, what happens is that the breeze slowly will increase the oscillation amplitude of your bridge. And at the end, the bridge will fall down. Go to internet. We have a film about this because this happened many times. At the end, they knew it was bound to fall. Okay. How to avoid this? Change or change. That's clear. And what you have to learn is that the lambda frequencies must be far from the expected external frequencies. Okay? Or, which is also possible, you must invent a system which is very resistant to large amplitudes or oscillations. But you know, it is rather difficult to go on a bridge which is oscillating a lot. Okay? So, how the study of planets became important for designing bridges. This could be the title of this lecture. Okay, we stop here.